Chapter 4 Stack Enqueuing. The stack ADT. A stack is a list with the restriction that insertions and deletions can only be performed at theta pop. The list the other end is called bottom. Fundamental operations, push, equivalent to an insert. Pop, deletes the most recently inserted element. Top, examines the most recently inserted element. 2. Stack ADT. Stacks are less flexible but are more efficient and easy to implement. Stacks are known as LIFO, last in, first out, lists. The last element inserted will be the first to be retrieved. 3. Push and pop. Primary operations: push and pop. Push, add an element to the top of the stack. Pop, remove the element at the top of the stack. Empty stack. Push an element, push another. Top, pop, top, top, A, B, A, top, A. 4. Implementation of stacks. Any list implementation could be used to implement a stack. Arrays, static, the size of stack is given initially. Linked lists, dynamic, never become full. We will explore implementations based on array and linked list. Let's see how to use an array to implement a stack first. 5. Array implementation. Need to declare an array size ahead of time associated with each stack. Is top of stack for an empty stack. Set top of stack to 1. Push 1. Increment top of stack B1. 2. Set stack top of stack equals x pop 1. Set return value to stack top of stack 2. Decrement top of stack B1. These operations are performed in very fast constant time. 6. Stack attributes and operations. Attributes of stack: max top, the max size off stack. Top, the index of the top element off stack. Values, element / point to an array which stores elements off stack. Operations of stack: is empty, return true if stack is empty, return false otherwise. Is full, return true if stack is full, return false otherwise. Top, return the element at the top off stack. Push, add an element to the top off stack. Pop, delete the element at the top off stack. 7. Display stack, print all the data in the stack. Create stack. Initialize the stack. Allocate a stack array of size. Example: size equals 10. Initially top is set to 1. It means the stack is empty. When the stack is full, top will have its maximum value, i.e. size, 1. Static int stack size max top int top equals size, 1, equals -1, 8. Push stack void push, const $x, push an element onto the stack. If the stack is full, print the error information. Note at top always represents the index of the top element. Push, int item, after pushing an element, increment top. Top equals top plus 1, if, top max top, / put the new element in the stack. Stack top equals item, else /, stack overflow, 9. Pop stack int pop, pop and return the element at the top of the stack. If the stack is empty, print the error information. In this case, the return value is useless. Int pop, don't forget to decrement top int del_val equals 0, if, top equals -1, /, stack underflow, else del_val equals stack top / store the topmost value in del_val. Stack top equals null, / delete the topmost value. Top equals top -1, return, del_val, 10. Stack top double top, return the top element of the stack. Unlike pop, this function does not remove the top element. Double top, if, top equals -1, lt error, the stack is empty. lt and l, return -1, else return stack top, 11. Printing all the elements. Void display stack, print all the elements. lt top gt, 4, int I equals top, igt equals 0, I, lt /t lt stack ilt /t and l, lt /t lt and l, 12. Int main, void, using stack push, 5.0, push, 6.5, push, -3.0, push, -8.0, display stack, Could LT top, LT top, LT and L, stack.pop, could LT top, LT top, LT and L, while, top, equals dash 1, pop, display stack, return 0, result 13. Implementation based on linked list need not know the maximum size add /access /delete in the beginning. 1. Need several memory access. Deletions create the stack struct node int item, node asterisk next, struct node asterisk top of stack equals null 14. Linked list push stacks algorithm step 1 create the new node step 2, check whether the top of stack is empty or not if so, go to step 3 else go to step 4 step 3 make your top off stack pointer point to it and quit. Step 4 assign the top off stack pointer to the newly attached element. 15. Push operation push, int item, nunit equals new node, nunit gt item equals item, nunit gt next equals null, if, top of stack equals null, top of stack equals nunit, else nunit gt next equals top of stack, 16 top of stack equals nunit. The pop operation algorithm, step 1 if the stack is empty then give an alert message stack underflow and quit, else proceed step 2 make target point to top off stack next pointer step 3, free the top off stack node, step 4, make the node pointed by target as your topmost element 17. Pop operation int pop underscore val equals 0, if, top of stack equals null, cuddled stack underflow, else node asterisk target equals top of stack next, pop underscore val equals top of stack gt item, delete top of stack equals target, 18 return, pop underscore val. Application of stack, balancing symbols to check that every right brace, bracket, and parenthesis must correspond to its left counterpart e.g., is legal, but, is illegal algorithm. 1. Make an empty stack. 2. Read characters until end of file I. If the character is an opening symbol, push it onto the stack too. If it is a closing symbol, then if the stack is empty, report an error 3. Otherwise, pop the stack. If the symbol popped is not the corresponding opening symbol, then report an error 3, 19 at end of file. If the stack is not empty, report an error. Example 20. Example 21. Postfix expressions calculate 4.99 asterisk 1.06 plus 5.99 plus 6.99 asterisk 1.06 need to know the precedence rules postfix, reverse Polish, expression 4.99 1.06 asterisk 5.99 plus 6.99 1.06 asterisk plus use stack to evaluate postfix expressions when a number is seen, it is pushed onto the stack when an operator is seen. The operator is applied to the two numbers that are popped from the stack. The result is pushed onto the stack. Example evaluate 6523 plus 8 asterisk plus 3 plus asterisk. The time to evaluate a postfix expression is n 22, 23, q24. Q overview QADT basic operations of enqueuing, dequeuing etc. implementation of Q array linked list 25. QADT like a stack, AccuAce also a list. However, with a queue, insertion is done at one end, while deletion is performed at the other end. Accessing the elements of queues follows a first in, first out, FIFO, order. Like customers standing in a checkout line in a shop, the first customer in is the first customer served. 26. The QADT another form of restricted list insertion is done at one end, whereas deletion is performed at the other end. Basic operations, enqueue, insert an element at the rear of the list. Dequeue, delete the element at the front of the list. First in first out, FIFO, list 27. Enqueue and dequeue primary queue operations. Enqueue and dequeue like checkout lines in a store, a queue has a front and a rear. Enqueue insert an element at the rear of the queue. Insert, enqueue, dequeue remove an element from the front of the queue. Remove, dequeue, front rear 28. Implementation of queue just as stacks can be implemented as arrays or linked lists. So with queues. Dynamic queue shave the same advantages over static queue assist dynamic stack shave over static stacks 29. Queue implementation of array. There are several different algorithms to implement enqueuing dequeuing naive way. When enqueuing, the front index is always fixed and the rear index moves forward in the array. Rear 3 3 6 3 6 9 front enqueue 3 enqueue 6 enqueue 9 30. Queue implementation of array naive way. When enqueuing, the front index is always fixed and the rear index moves forward in the array. When dequeuing, the element at the front the queue is removed. Move all the elements after it by one position. Inefficient. Rear equals -1699 front dequeue 31. Queue implementation of array better way. When an item is enqueued, make the rear index move forward. When an item is dequeued, the front index moves by one element towards the back of the queue, thus removing the front item, so no copying to neighboring elements is needed. Front, thirksuo, rear, thirua, after one dequeue, and one enqueue, thirksu, after another dequeue, and two enqueues, thirks, after two more dequeues, and two enqueues. The problem here is that the rear index cannot move beyond the last element in the array. 32. Implementation using circular array. Using a circular array. When an element moves past the end of a circular array, it wraps around to the beginning, e.g. 07963 07963, after enqueue 4, after enqueue 4, the rear index moves from 3 to 4. 33. 34. Empty or full. Empty queue back equals front one full queue. The same reason, and values to represent n+1 state solutions. Use a Boolean variable to say explicitly whether the queue is empty or not. Make the array of size n+1 and only allow n elements to be stored. Use a counter of the number of elements in the queue. 35. Queue class attributes of queue front/rear index counter, number of elements in the queue, max size, capacity of the queue. Values point to an array which stores elements of the queue. Operations of queue is empty, return true if queue is empty, return false otherwise is full, return true if queue is full, return false otherwise. Enqueue, add an element to the rear of queue dequeue, delete the element at the front of queue. Display queue, print all the data. 36. Create queue in size equals 10, allocate a queue array of size. By default size equals 10. Front is set to 0, pointing to the first element of the array. Rear is set to 1. The queue is empty initially. Queue in size / equals 10 *, values equals new double size, max size equals size, front equals 0, rear equals -1, counter equals 0, 37. Is empty and is full. Since we keep track of the number of elements that are actually in the queue counter, it is easy to check if the queue is empty or full. Bool queue is empty if counter return false, else return true. Bool queue is full if counter lt max size return false, else return true. 38. Enqueue bool queue enqueue double x if is full, could lt error, the queue is full. lt and l return false, else / calculate the new rear position. Circular rear / insert new item equals rear +1% max size, values rear equals x / update counter plus return true. 39. Dequeue bool queue dequeue double and x if is empty, could lt error, the queue is empty. lt and l return false, else / retrieve the front item. X equals values front / move front equals front +1% max size / update counter return true. 40. Printing the elements could lt front gt 4 int I equals 0, ilt counter I plus if I equals 0, could lt /t, else could lt /t /t. could LT values, front plus I, percent max size, if I equals counter, 1, could LT and L, else could LT backslash TLT rear LT and L, void Q display Q, 41. Int main, void, Q dot enqueue, 5, Q dot display Q, double value, Q dot dequeuing, value, could LT retrieved element equals LT value LT and L, Q dot display Q, Q dot enqueue, 7, Q dot display Q, return 0, using QQQ, 5, could LT enqueue 5 items LT and L, 4, int x equals 0, x LT5, x plus plus, Q dot enqueue, x, could LT now attempting to enqueue AGA in LT and L, 42. Q implementation based on linked list class Q public, Q, / constructor front equals rear equals null, counter equals 0, Q, / destructor double value, while, is empty, dequeuing, value, bool is empty, if, counter, else return false, return true, void enqueue, double x, bool dequeuing, double and x, void display Q, void, private, node asterisk front, node asterisk rear, int counter, / pointer to front node / pointer to last node / number of elements, 43. Enqueue void Q enqueue, double x, node asterisk new node equals new node, nunit theta equals x, nunit next equals null, if, is empty, front equals new node, rear equals new node, else rear next equals new node, rear equals new node, counter plus plus, rear 5 rear new node 85844. Dequeuing bool Q dequeuing, double and x, if, is empty, could LT error, the Q is empty LT and L, return false, else x equals front theta, node asterisk next node equals front next, delete front equals next node, counter, 38 front 85545. Printing all the elements void Q display Q, could LT front GT, node asterisk ker node equals front, 4, int I equals 0, ILT counter, I plus plus, if, I equals 0, could LT backslash T, else could LT backslash T, could LT ker node data, if, I, equals counter, 1, could LT and L, else could LT backslash TLT rear LT and L, kernode equals kernode next, 46. Result Q implemented using linked list will be never full based on linked list based on array 47. End of chapter 448.